Hello everyone, welcome to this video. In the previous video we have seen logic circuits and data representation, data types and a microcontroller system. In this video let us understand the next concepts, that is realization using basic gates and then half adder, full adder, multiplexer, demultiplexer and encoder and decoder. So the first thing is realization using basic gates. How to realize any digital circuit using basic gates? The basic gates are NOT gate, AND gate, OR gate. These three are the basic gates. We call these three as basic gates. Why? Because we can realize any digital circuit using these three. So let me take an example like y is equal to a dot b plus c. Now if we have a function like this or the expression like this, how to implement this using basic gates? First we need to look at this expression. Here we will be having a dot b and then plus c. This can be written as a dot b plus c. We can also write like this. Now we can realize this a dot b first and then we can use plus c. What is the functionality for this dot? It is an AND functionality, logical AND. This plus carries OR functionality. So now we can write the circuit easily by using the two inputs. For one 2 input AND gate with inputs are A, B, this gives A dot B. Now we got A dot B, we will be having plus C here. So take one more input C and we can use OR gate for getting plus logic plus functionality. So this is A dot B plus C. By using this method, you can write any digital circuit which is having an expression like this using basic gates. Then the next concept is adder. Adder is a device that will add the two inputs together. To add the two inputs, two binary values, we can use an adder device. Here it gives the result as sum and carry. We know that if we are going to add any two values, we will be getting the sum. If this exceeds, we will be getting carry over here. So by this method, we can have two adders. One is the half adder, another one is full adder. What is half adder? Here you can observe this is the block diagram of the half adder. In this block, we will be having a circuitry which is functioning as half adder. We are represented with a bounded box here. This half adder is adding 2 bits as I said, and the output will be 2 bits. Let me take the input as A and B. A can attain a value 0 or 1, B can take value 0 or 1. So if we add these values, we will be getting sum and carry. To generate sum and carry, we will be having two outputs. Similarly, what is full adder? Full adder will be also adding two inputs, and if any carry coming from the other adder, if the carry coming from the other adder has to be added with this, so here we will be having carry bit C in. Now let us treat this as the third input. Now we can say we will be having 3 inputs to the full adder and outputs will be same as half adder, that is sum and carry. So here what we understood is that there will be a device called half adder. It will add 2 inputs, one is A, another one is B, and it will generate the output as sum and output as carry. If the third input comes into picture, let me treat it as C in, and sum and carry will be generated by using full adder. Now let us understand the half adder functionality. This is the block diagram of the half adder. I am treating the two inputs are A, B and output is sum and carry. If we assign values for A and B, what are all the different values we can take? We can take A as 0, at the same time B as 0. We can take A as 0, at the time we can take B as 1. This is the another case of input. Similarly, I can take A1, B0 and A1, B1. Here if we take these values and if we keep on adding these two, 0 plus 0 is 0. There is no carry generated. Here also 0. 0 plus 1, if we add 0 and 1, we get 1. There is no carry generated. That's why sum is 1, carry is 0. Similarly, input 1 and input 0, 1 plus 0. 1 plus 0 is 1, carry is 0. When we are adding 1 plus 1, what is 1 plus 1? if you add 1 plus 1 in decimal, it is 2. Similarly, in binary, if you add 1 plus 1, we need to represent this 2 as 1 0. Means this 0 is sum and 1 is carry. That's why here we are writing 0 and in place of carry we are writing 1. Now we need to write the expression for this sum as well as carry to get the circuit for half adder. Wherever sum is 1, we need to consider those inputs. Wherever carry is 1, we need to consider those inputs to write the expression for sum as well as carry. First, let us write the expression for sum. How to write the expression for sum is 1 here and also sum is 1 here. So, what are all the inputs in this case? We will be having 0, 1. So, let me write 0 as a bar into b is 1. That's why I am going to write it as b as it is, plus the next set of values where we are getting sum as 1. Here sum is 1, right? In this case, we will be having the inputs 1, 0. Means 1 can be written as a and b is 0. It can be written as b bar. It is a into b bar. This is the expression for sum. Similarly, look at the carry now. Write the expression for carry. Wherever carry is generated as 1, we need to consider those inputs. Carry is 1 here, the inputs are 1 and 1. So, 1 and 1 means it is a dot b. So, these two are the expressions for sum and carry. What is the expression for sum? A bar into b plus a into b bar. You can recall while explaining the logic gates, I told the expression for XOR gate. The XOR gate expression is y is equal to a bar b plus a b bar. Means we can generate y by using this expression. The expression is same for sum. So we can use input A, input B, and if you put one XOR gate, this gives the sum. It is very simple to write sum. Similarly, carry. How to write carry? Carry is getting generated by the logic AND between A and B. So use the same inputs A, B, take input A and take input B, put one AND gate, it gives carry. Right, this is the circuit, or we say this is the gate level circuit for half adder, right? Now we can write these circuits for any digital circuit if you know the expression. How to write the expression? By looking at the truth table. How to write the truth table? We need to know how actually the functionality will be, right? Now let us see the next adder. Okay, this is the circuit I have written already here. Now let us see the full adder circuit. The full adder is the adder again. It will take the two inputs as A, B, and the one more input here we are going to consider, that is Cin. What is this Cin? If the two adders are connected like this, let us take this as one full adder, this as another full adder. If we have two inputs like AB here, if we have two inputs like AB here, if the sum generated will be taken like this, here also sum will be taken like this. If carry is generated, what we are supposed to do? We need to pass to the next adder for consideration. Suppose if we are adding 12 plus 39, what we do? We are going to add 9 plus 2, that is 11. We are going to take the carry over here. To the next adder, we are going to consider this carry. This is the third input now. So 3 plus 1, 4 plus 1, 5. This is how we are going to do the calculation. Similarly, the carry of this particular adder will be taken into consideration for the next adder. So here the next adder is full adder. Let us assume that scenario and consider this third input Cin. If third input comes, it will be called as full adder. Okay. The full adder output we are going to see now. This is sum and this is carry. How to add these three? 0 plus 0 plus 0 is 0, carry is 0. 0 plus 0 plus 1 is 1, carry is 0. Again 0 plus 1 plus 0 is 1, sum is 1, carry 0. 0, 1, 1 means 1 plus 1 is 2. 2 can be represented as 1, 0. In 1, 0, we need to treat this as sum and this as carry. That's why carry is 1 and sum is 0. Don't get confused. 0 plus 1 we are adding. If we consider it decimally, it is easy for us. So decimal it is 1 plus 1 is 2. We are going to represent it as 1 0. So this is sum and the extra bit, the next bit is carry. That's why it is 1 here and 0 here. And again next values 1 0 0 gives sum 1 carry 0. 1 0 1 is 2, again carry is 1, sum is 0. Similarly here also we will be having 2 ones, so carry 1, sum 0. When 1 plus 1 plus 1, how to add 1 plus 1 plus 1? 1 plus 1 plus 1 is 3. How to represent 3? 3 is 1 1 in binary. So this is sum and this is carry. That's why sum is 1 and carry is 1. This is the truth table for sum as well as carry generation. Now we got to know how actually the addition will be done for 3 inputs. By using this sum as well as carry lines, we need to write the expression for sum and carry in the similar way how we did in half adder. Okay, now how to write the expression for sum? Mark all the outputs in sum where it is generated as 1. So for this one we need to take these 3 inputs into consideration. This 1 is generated by using A is 0, B is 0 and carry is 1. That's why I am going to write, if it is 0, take bar, A bar, B bar, A dot, bar, B bar, dot, C plus. The next value 1 is generated here. So these 3 values are 0, 1, 0. In place of 0, let me write it as bar, dot, B dot, C bar. The next value is 1 here. It is 1 0 0. 1 0 0 means A, B bar, C bar plus. Next we will be having here, it is A, B, C. Now we need to simplify this expression. There are different Boolean laws to simplify the complex expression into simple one. If you simplify this expression, finally it will be reduced to A plus of B plus of C. What is A plus of B? A plus of B is XOR gate. You can recall again the XOR gate. It is A bar B plus A B bar. This can also be written as A plus of B. Means here we will be having A plus of B plus of C. Means it is a 3 input XOR gate. 3 input XOR gate is sufficient to generate sum using full adder. Now let me write the carry expression. How to write carry? Carry is 1 here because of these 3 inputs. It is A bar, B and C plus carry is 1 here. So I need to treat these 3 A, B bar, C, A, B bar, C plus for this output 1 it is 1 1 0. 1 1 0 is A is 1, B is 1, C is C bar. And because of this one, here all 3 are 1s. So let me write it as A, B, C. Again this is a complex expression. We can simplify using Boolean laws. Okay, we can simplify using Boolean laws. If you are interested, you can learn these Boolean laws and you can simplify this carry expression. Finally we are going to get the carry output as AB plus BC plus CA. If you are taken C in here, wherever C is there, we can replace that by C input. No issues. Right? Similarly here also we are going to get C in and C in. Wherever C is there, I just replace that by C in. Since we have represented in the truth table it has C in and also in the block diagram it is C in. Okay. Now we can write the circuit for this sum as well as carry. Sum can be generated by using 3 inputs A, B, C, and we are going to connect that to the XOR gate. This is XOR gate, it is generating sum. Okay. Similarly, carry expression is there. We need to implement this carry expression by taking input A, input B, use one AND gate to generate A dot B. Now this is generated. Then we need to choose this B dot C in, take this B and take C in put one more AND gate, it gives B dot C in, and then we will be having plus C in into A. Take this C in as it is and take this A from here. So this gives C in into A. Now we will be having plus out of these three. Plus in the sense it is logical OR gate. If you put one OR gate here, it gives the carry, right? So carry expression will be this, and we have implemented using the logic gates. Similarly, the sum. This is 3 input XOR. Okay. So you can observe here, this is the sum and this is carry. By using XOR gate over here and AND gate combinations and OR gate combinations, we have written the logic circuit. Then we can also generate this full adder circuit using two half adders. Obviously, half adder is a device, it is going to add two inputs and it gives two outputs. Since the third input is there, we can take the output of this into consideration, means the sum will be taken into consideration for the input of the next half adder, and this C will be taken into consideration as another input, and we can generate the sum and carry by using one OR gate at the output. Okay, this is the another way of writing the full adder if the half adder module is available with us. Otherwise, we need to design this half adder and then we can put over here to get the final full adder circuit. Here also full adder using two half adders, the truth table is same. This is also a full adder implementation what we have seen earlier, but in the different way. Next we have multiplexers. What is multiplexer? Multiplexer is an electronic device. It will select one signal as output from 2 power n inputs. You guys know 2 power n inputs in the sense 2 power 1 is 2, 2 power 2 is 4, 2 power 3 is 8. Similarly 2 power 4 is 16, like this. So what is multiplexer means? Multiplexer will be having the inputs like this. It is in the order of 2 power n. We may have 2 inputs or 4 inputs or 8 inputs or 16 inputs, and output will be only one output. It will be having 2 power n inputs and only one output. And what is this one output? Out of these inputs, why it is only one output means at one time this multiplexer is going to pass the output by selecting any of these inputs. Means only one input is selected at a time and output will be generated whatever the input is there. That will be selected by select lines. This is n. What is n here? If we have 2 power 2 4 inputs, if we have 4 inputs, we need 2 select lines. If you have 8 inputs, we require 3 select lines. If you have 16 inputs, we require 4 select lines. These select lines are again the inputs. By using the combination of these, we are going to choose which input line should connect to the output. Now let us understand this in a better way by writing the circuit. This device is also called as data selector. Why it is called so means there are data coming from different domains here, or the different circuits the data is coming from. We need to choose only one at the output. Means the better example for this is, let us take our TV cable or TV broadcasting, where we are going to get different channels. We are going to get many channels and it will be multiplexed and it is passing through a single cable. The cable coming to the television is a single line. It will be consisting of multiple channels, right? Once we choose the particular channel, suppose if we take this channel with a code which will be given through the remote, it will be selected as output, right? This is the practical example of this multiplexer. Now let us understand this in a better way. Let us consider I0, I1, I2 up to IN. We will be having multiple data inputs. There will be a data selector in between. This will choose only one input line or one data out of these n inputs at a time, right? So you can observe here this red line indicating it is selecting this particular input. So this is the line which is connected into output now. Whatever the data in I0, it will be available at Q. Similarly, if you have different inputs, this select line will be having data selection lines here as input to this system. If we have different values over here, we can choose these inputs. Suppose if we call this as 0th system, first system, second system, similarly n system. If we give 0 over here, it will choose this. If we give 1 over here, it will choose the first system. If we give 2, it will choose the second data, like that. You can observe here in this circuit again, it is showing how the data will be selected. Suppose if we have a data called ECE, EEE, ME and CS. We need to choose only one at a time. Now if we pass 0, 0 from select lines, it will choose, let us take ECE. Suppose if we give the value as 0, 1, it will choose EEE. If we choose 1, 0, if we give 1, 0, we can choose ME at the output. If we give 1, 1, we can choose CS as output. So this select line is inputs are going to make the change in the data selector where it will connect to these input values. Then we have different multiplexers. Out of those, first one is a very simple one, 2:1 MUX. Why it is represented or called as 2:1 means it will be having two inputs. This is the representation of number of inputs. This is the representation of number of outputs. Any MUX system will be having multiple inputs and single output. Okay. You can observe here, this is the MUX diagram. We can write the MUX like this. Why? Because more inputs are there, only one output. That's why we are going to represent in this way. Let it be. So the two inputs are AB here. Since it is a two input and one output device, two inputs I am calling it as AB. And there is a select line, I am representing it as S0. So this is S0. And there is one output is Z. When this select line is 0, when we are giving select line or the control input as 0, it will select input A to Z, right? So Z becomes A. Whatever the value present in A will be available in Z. If we choose 1 over here, B will be selected as output and B will be at the output Z, right? So how to write the circuit for this? Let me write the circuit in the same way how we have written for half adder and full adder, by using a expression. How the expression is written? By using the truth table. This will be called as the truth table, right? Whenever the true values are there, why it is called as truth table means it will give in which case the output is true, in which case the output is false. Okay. How to write the expression for Z? We need to get A when S0 is 0. So A is my output when S0 is 0. It is S0 bar. Plus B is my output when S0 is 1. So this is the expression we are going to get for 2:1 MUX. How to write the circuit? Take A as input, take B as input, and also we will be having S0 and S0 bar. So A into S0 bar is there. Let me take S0 here and generate one S0 bar using NOT gate. This is NOT gate generating the complement, right? And this is A, this is B. A into S0 bar I am supposed to connect. So this is A and this is S0 bar. I need to put one AND gate. This AND gate gives A dot S0 bar, right? And here we will be having B dot S0, right? This is S0. I am taking this S0 here. This is B. I put one more AND gate and this is B into S0. Now we will be having plus in between. So connect these two with OR gate, one OR gate. So this OR gate is a plus functionality. This gives the output Z, right? This is how the 2:1 MUX can be written. Similarly, we have 4:1 MUX. It is 4:1 where A, B, C, D are my inputs. And there are two select lines required here. Why? Because 2 power n inputs means here we will be having 4. This is 2 power 2. Here 2 power n inputs are there. N select lines will be there. This is the meaning of the 4:1 any multiplexer. If the 2 power n inputs are there, where n indicates the select lines. If 2 power 2 inputs are there, means totally 4 inputs are there. Here 2 select lines are required. That's why I am calling it as S0 and S1. Here we have S0 and S1. There are 4 possible values we can give S1, S0 from S1 and S0. It is simply as I can pass 0, I can pass 1, I can pass 2, I can pass 3. 0 will be indicated as 0, 0, 1 can be indicated as 0, 1, 2 can be indicated as 1, 0, 3 can be indicated as 1, 1. When 0, 0 is given, A will be selected at Y. So Y is equal to A when 0, 0 is given as input from this. 0, 1 is given as input, B will be the output. 1, 0 is the input from the select line, I need to select C. And 1, 1 is selecting D. Similarly, if you write the expression for this, Y is equal to A into, when A is selected, S0 bar and S1 bar are there. Plus when B is selected, we will be having S0 and S1 bar. Similarly, C will be selected when S0 bar and S1 is there with that. Similarly, D with S0 and S1. So again write the circuit for this. Okay. Take A, B, C, D into consideration. Write the circuit by generating S0 bar. Using S0, put one NOT gate. This gives S0 bar. Similarly for S1, put NOT gate. It gives S1 bar. And by using A line, B line, C line and D line, we can have a circuitry of 4:1 MUX. Okay, you can connect using basic gates. So we will be getting output Y. You do it yourself. Then we will be having 8:1 MUX. Here we will be having total 8 inputs. 8 means it is 2 power 3. That's why 3 select lines are there, right? So the select line inputs can be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, right? These are the different values we can get for 2 power 3 inputs, means using 3 select lines. Using 3-bit values, if we represent, it will go up to 0, 1, 2, 3, 4, 5, 6, 7 like that. Okay. So the outputs are I0 when 0, 0, 0. Here it is I1. Here it is I2. I3 will be selected. I4, I5, I6 and I7 will be selected when the inputs are given like this. If you write the circuit here as shown, the circuit will be. These are NOT gates, if you observe, and these are AND gates, and this is one OR gate they have used for plus. Then we have demultiplexer. The same functionality can be done in the reverse order. Means, as I said, if you have a single line, by using demultiplexer, we can split into 2. Here this data line is carrying a input, and we can able to get that input in 2 output lines. In which output line we are supposed to get will be decided by this select line. So here you can observe this is input D. Here we can have D as 0 or 1. Okay. When select line is 0, when S is 0, this Y1 will be getting our value D. What is D? When S is 0, Y1 will be getting the value, it is 0. Since Y2 is also 0, we are not getting understanding whether it is 0 is transferring to Y2 or Y1. Now let us take this condition. When D is 1, when S is 0, which output it should select? It should go, this 1 should be appear in Y1. So Y1 will be 1. You can observe Y2 is 0 itself. Now when S becomes 1 and input is 1, this input is 1 now, this S becomes 1, it should select Y2. Y2 becomes 1 when the select line is 1. This is 2 output and 1 input demultiplexer. Similarly, we will be having 1:4 Demux, reverse order to the 4:1 MUX. Here also 2 select lines are there. When it is 0, 0, if the input 1 is available, it will be pass in D0. If 0, 1 is there, it will appear in D1. If 1, 0 is the select line, we are selecting D2. If 1, 1 is the select line, this one will be appear in D3. This is how we can have demultiplexer also. Then we have encoders and decoders. In your syllabus only decoder is there. Let us understand both. Encoder is a device which is going to encode 2 power n inputs to n outputs. Again I said 2 power 3 inputs are there, it will be encoding that to 3 outputs. In MUX, we will be having, if you have 2 power 3 inputs, 3 select lines are required, right? That is n. But here don't confuse with the encoder and the multiplexer, where I told you to choose the select lines depending on this n. Here in the encoder, the outputs are n and 2 power n inputs are there. Okay. This encoder and decoder can be used in any encryption and decryption methods. You can recall the ATM pin. The ATM pin which you have given something like 1, 2, 3, 4 is the number which is having. This will be encoded and stored in the system. Once you enter 1, 2, 3, 4, that will be decoded and the computer will come to know that the legitimate user is accessing to the ATM, and it will give the information of your own account, right, where the encoder and decoder is used. So this is one of the example of 3 to 8 decoder. Here 3 inputs are there, you can observe. It will be decoded to 8 outputs. Okay. So if the input is 0, 0, 0, I am decoding it to all zeros, and here it is 1. If 0, 0, 1 is my input, I am decoding it to all zeros and 1, 0. Similarly, if you observe, this 1 is transferring to the next value. So we will be having 3 inputs here and we are converting that into 8 outputs. Okay. In the similar way, we will be having 8:3 encoder also. If you have more inputs, that is 2 power n inputs, this is 2 power 3, we will be having 3 outputs. Okay. So encoder will be doing the reverse functionality. If you have all zeros, okay, and 1, it will be encoded to 0, 0, 0. That is encoder. So this decoder can be written like this. If you write D0, D1, D2, D3, D4, D5, D6, D7 expressions, here D0 is 1, you can write it as A bar, B bar, sorry, A0 bar, A1 bar, A2 bar, like that. If you write the expression, you can get the circuit like this.